start. So the next topic is called potential. So the symbol we use is small v or capital V depending on the situation. So generally the small v is the way to represent potential, and the capital V we use to represent potential difference or voltage. So voltage is the term that you will frequently encounter in a chapter called current and electricity. But as of now, we'll only discuss about the potential. And the voltage is nothing but the difference of potential between 2 points of a circuit. Generally, the context will be circuit. So when I say potential, then potential can be defined for any charge. So it is not like we need to charge because this is not about interaction. It is about the sole presence of charge and the effect it creates around itself. So the moment you bring a charge in space, what it does is it creates a field around itself. Okay. So let's say if I call this as infinity. If this is infinity, and if you wish to bring any, let's say this is the source charge. And this is the test charge. So if you're trying to bring this charge in in the field of the existing charge at a distance, let's call it r, from the given charge, we know the work done required is how much?
KQ by R.
So KQQ by R is the work done required, right?
Yes, sir.
So you need to have, spend this much energy. You have to invest this much energy to bring this charge here. So potential talks about like what is the work done per charge. So potential is defined as work done in bringing a charge from infinity to a certain point in an existing field due to a given charge plus q. So this is defined as work done per charge. So when you define something for the unit charge, then the term becomes potential. So it is like a rate card, rate list. You can say when you go to a grocery shop, you know items are listed like this rupees per kg, or this much amount per piece, okay, or per dozen. So there is something called per, which means you talk about the rate. So how much money you need to invest per charge is called potential of the point P due to the given charge capital Q. So going by this definition, we can add the potential at a point P is K. We know the work done already, and because we are looking for the per value, then the answer is definitely the potential will be KQ by R. Again, it is a scalar quantity, so we have to be careful. It's a scalar. So it is a scalar quantity, and the formula is KQ by small r, which means a charge of value Q will create a potential of this value around itself at a distance r. So r is the distance from the charge. If you try to capture every point at the same distance from Q, then what will get?
So at every point at the distance R from Q, it will be KQ by R only.
Yeah, so it means the shape of the point, if I join all such points, then the shape will turns out to be?
A circle.
No.
Sorry, a sphere.
Exactly. So this is a simply a sphere around the charge. It's a sphere, and this entire sphere will talk about a single potential value, no matter where you talk. So which point you choose. So the potential anywhere on this sphere will have the same value because it's a scalar quantity. So there is no direction involved, which simply means that no matter from which direction you land, if you come at a distance r from the given charge, the work is fixed and so the potential. So this is like a, any concentric sphere that we can draw around the charge will represent a surface. Understood?
Yes, sir.
So every surface around the point charge will represent a surface, and this surface will be having same potential. So we call such surface as equipotential surfaces because they represent constant potential. Now, if you go from one surface to other surface, the answer will change. But if you roam around the same surface, the potential cannot change. So such surface we can call
Equipotential surface.
equipotential. So what we can say that a charge is capable of creating equipotential, a point charge. So point charge is capable of creating equipotential surfaces around itself, and these surfaces will be represented by some imaginary hollow sphere, and each surface will have constant potential value. Also, from the concept of electric field, we know that electric field will be readily outward if it is a positive and readily inward if it is a negative charge, right?
Yes, sir.
For the time being, if I say this as E, this is a positive charge, then the E will be like this.
Yes, sir.
And what we can realize as of now that by drawing such a field, we can clearly see the angle between the equipotential surface and the field at any point is always perpendicular. So this is the first takeaway that we must understand that the field lines are always perpendicular to the equipotential surface. What do you say?
Field lines are always perpendicular to the equipotential surface. So
Correct.
is surface like an area, like area vector can be
Yeah, surface
considered?
surface means at a point. You choose one particular point of the surface. So
So we
at that
consider
point,
the
yeah,
tangent to it, sir, as the direction of the surface.
surface will be tangent. Surface means area vector is always perpendicular. No?
Yes, sir. So
So no
when we
matter,
say equipotential surface is perpendicular to the electric field line,
it means every surface which you consider, if you choose any point of the every surface, that will at that point the electric field will be normal to the plane of the surface at that location. If I choose a small patch here, the electric field is normal to this patch. Understood?
yes, sir.
It is also normal to this patch, which is part of the other surface. It is also normal to this patch, which is part of the other surface, and you can draw infinite such lines, right? Infinite electric field lines.
Yes, sir.
So when I say it is normal to the equipotential surface, it means for any random point taken on the equipotential surface, if you try to look at the electric field at that location, it will be perpendicular. Of course, not all points will have different direction, but for a given point, it will be perpendicular. Point means, of course, elementary area. Okay, elementary area of the surface. Okay,
Okay, sir.
so this is a very famous, you can say, statement. You should remember that uh, electric field lines.
So, but if we are considering an elementary area and we are comparing it to a vector, shouldn't we also compare it to like the elementary area vector?
The area vector will be parallel. You can say for area vector, you can say parallel. When you say
Sir,
the area vector, it's parallel. When you say area, which means the surface, then it's perpendicular.
okay, sir.
So electric field lines are always perpendicular to equipotential surface. I'm not talking about the area. I'm talking about the surface. Surface means simply means just a surface. No vector thing attached to this.
Okay, sir.
Electric field lines are always perpendicular to equipotential surface. Okay. So this concept is very useful, and we will try to use it as and when to prove certain things in future.
Okay, sir.
Okay. So how the fundamentally every charge creates equipotential surface. In our case, the things are simple because we have a point charge. In complex charge distribution, it will be very difficult to figure it out the equipotential surface. Sometimes we can figure it out easily, sometimes it's difficult. So if these are equipotential surface at distance A, B, C, it means they will have same potential. And what we can say that the direction of field lines is always on the high potential to the low potential, isn't it?
Yes, sir. The repulsion, I mean, like the field lines are more concentrated near to the charge.
So we can also say that the closer the, because the potential formula is kq by r. So if r is small, then v is larger, right? Assuming q
Yes,
is
sir.
positive. So we can say that if this is v1, this is v2, this is v3. So we can clearly say v1 is more than v2. So the most fundamental thing in nature is charge. Charge creates potential. Potential difference creates electric field. Electric field creates force, which in turn may create acceleration and then velocity and then displacement. So if you look at the fundamental, like most fundamental towards the terminology, so we can say charge is the most fundamental. Charge produces potential. Potential creates electric field. Or you can say the difference of potential creates the
Electrics.
electric, and then field creates the force. So that's a sequence of thinking that we should have. So if we have a two surfaces which are having same potential, it means the surface one is having potential same as surface two. Then between such surface who are at same potential, we cannot have electric field lines. Understood? It is simply not possible.
Sir, as in like from one, like one for V1, one part of the sphere to like the other part, we can't connect a
Yeah, yeah.
electric
Because
field line.
the electric field has to flow from high to low. So if you have a space in which nothing is high, nothing is low, then how it will flow?
Nothing will flow.
So the idea is if I create a surface like this, and if I say this is at potential V and this is also at potential V, so we cannot expect any electric field between the surface.
Yes, sir.
It can be outside. It can be outside and at the right angle. And as per the definition, it must be normal to the surface at a point. Okay, so that is okay. But we cannot talk about the electric field between the two surfaces which are equipotential. So by some reason, if it is so, then we cannot draw any field lines. No field lines will be present. Okay. So later on, we will come to know again that a conductor, the volume of a conductor is always equipotential volume. no matter where you go in the volume, every point will have same potential. And that is the reason that a conductor always creates the field only outside the surface. Within the volume of conductor, we cannot have electric field at all because it will always keep the potential same. This is one way of thinking. Otherwise, because there is no field, so potentially same. Okay.
Yes, sir.
Now the second thing is if we have two surfaces which are equipotential themselves but not having same potential as compared to the other surface. So let's say if I have one surface, random surface, it may be three dimensional, but I'm just showing you two dimensional. So if we have a surface with potential V1 and if we have another surface with potential V2, so let's say the V1 is equipotential, V2 is equipotential. Then the electric field will be between the surface. Field will
Yes.
exist. Okay, so electric field will exist between the surface, and of course beyond is always possible, but it will also have the value between. And depending on which surface is bigger, the direction will vary accordingly. So it will be from
High
high
to
to
low.
low, or low to high. The only thing which you should be like aware of, that if they give you the options A, B, C, D, just check the option in which the field lines are coming perpendicularly.
Okay, sir.
So let's say field lines are like this. It must leave the surface at right angle and must hit the surface at right angle, because if it is at not at right angle, then it will violate the very notion of equipotential surface and the field relation.
Yes.
So equipotential surface and fields are always perpendicular. We'll also prove it mathematically very soon. But this is the thing which you need to be, concerned about, that what I should look for to eliminate the wrong options. The answer is simple. To eliminate the wrong option, just look at the beginning of the field lines and the termination. And if it is not at right angle, you can always say, okay, this is not the right answer for sure. So it is very difficult to actually plot the exact field lines for a complex situation. We cannot say anything. But when they give the option, then we can at least eliminate. So because we know certain rule about them. So with simple observation, we can rule out the wrong options from the right one. Okay, is clear?
Yes, sir.
So
Yes, sir.
if I come back to the problem of again electric field lines. So if we have a sphere which is symmetrically positively charged on the upper half and negative charge on the lower half. Okay, and the charge distribution of the positive and negative are equal. Okay. And if we choose any point on this axis, the axis which I've drawn, so be it any point P here, the potential contribution from the above and the below will exactly cancel out, right?
Yes.
So no matter which point we choose, the potential is going to be zero because
Zero.
of symmetricity,
Yes,
right?
yes.
The entire plane cutting in fact, the reality is the plane which you can draw the entire plane which you can draw will have same potential no matter where you go, isn't it?
Yes, sir.
And that is why So if it is exactly cutting into half, then every point in this plane will have a zero potential. So this is the equipotential surface of value zero. Okay.
Yes, sir.
So we can clearly say that the electric field at any of the point will be perpendicular, and because the top is positive and bottom is negative, so it is going to be like this. So on this surface, the field must be at right angle near the surface, right?
Yes, sir.
Because if it is not so, then it will violate the whole idea of equipotential surface.
Yes, sir.
And if you remember, the question was the same. So in the JE, they had given the four options in which the electric field lines was drawn like this. Let me read it for you.
From the positive to negative.
Yeah, and while crossing the equipotential surface, it must become perpendicular, right?
Yes, sir.
So it was like so they have drawn, okay, because the conductor surface itself is equipotential, so it will begin also at right angle.
Yes, sir.
So it will hit, it will leave at right angle, will again come back here, and again while crossing it will become right angle. Then it will go this way and will hit back the surface again at right angle. So this was the kind of diagram you might have seen.
Yes, sir.
So this is how we understand what is the right. So at least among the given options, we can eliminate the wrong one. So we may not be able to draw the exact lines, of course, but we can at least eliminate the wrong option, right?
Yes, sir. Sir, doesn't it like go inside?
Oh, my bad. Yeah. Just change that arrow like this. Okay.
Yes, sir.
So the idea of equipotential surface is very important. So conductor surface by default is equipotential, and so the electric field lines will follow the perpendicularity logic everywhere. So it will leave the surface at right angle and will terminate with surface at right angle. And if you can see some plane or a point or a line or locus whose potential is constant, then the field at that locus will be at right angle. Okay.
Yes, sir.
Okay. So you will come across question like this. We'll come to that very soon.
Sir, can you just come back in a minute?
Okay, sure.
So
Yeah. So again, coming back to the potential, if we have a charge Q, then it will create a potential like this. And we are already aware that the electric field at the point P is how much? KQ by R
KQ
square.
by R square.
So we can relate something from here. So if you look carefully, if you differentiate the V with respect to R, we get minus KQ by R square, right?
Yes, sir.
Which clearly says something that the electric field or the potential gradient, we call it potential gradient, is equals to minus E. So this is a very simple relation. So the heading was a relation between E and V. So we can say E equals to minus dV by dr. This is for one dimensional thing. We can write like this. We'll try to make it more generalized and we'll try to understand what does it mean exactly. So first of all, electric field is a vector quantity and potential is a scalar quantity. So we cannot relate a vector with a scalar. So what we are relating is actually the component of electric field with vector, with potential. So this is a radial field, and what you are getting is a radial component ER, you can see. And the value of ER is simply minus dV by dr. So we are trying to find the component of field in in a given direction. The whole idea is if we move in certain direction and if we see there is a difference of potential, we can say for sure there must be some component of field in that direction, isn't it?
Yes, sir.
Because potential difference is only possible if we have some field or vice versa. If there is a
Yes, sir.
field, it means difference must be there. So we say that if you walk along a direction, that's called R direction. And if I see there's a difference of potential, I can certainly say there is a field in that direction, or at least there is a component of field in that direction. I'm not sure about the net field. I'm just only sure about the field component in the given direction. Understood?
Yes, sir. Sir, potential is defined for a point or a charge, sir.
It is defined for a point due to a given charge. So this is a charge.
So, but then E is defined for like a point.
Yeah, E is also defined for a point. So this is the charge, and you're trying to find the potential at a distance r, right?
Yes, sir.
So potential at a distance r is point only, na?
So it's a point, but then it's only due to Q. But what if there were multiple
Yeah.
charges?
If it is multiple charge, then we have to take the vector, sorry, the algebraic sum of all potential. So we'll make it net potential. Okay.
Okay, sir. And the field will also be the net field.
Yeah, field will be also. Then it will definitely. So these relations are for net value.
Okay, sir.
And V is also representing the net value. So we are taking single charge to demonstrate only, but it will be true for any number of charge particles.
Yes, sir.
So let's say if you walk slightly ahead, and I call this as dr ahead. So at a distance r, we have a potential V. If electric field is in this direction, then at a distance r plus dr, we must have a new value. So we can call it V plus dV. So r distance potential is V. R plus dr potential is V plus dV, and electric field is readily away. So which one is high potential? This one or this one?
So V has high potential.
So electric field is defined in the direction of R. The component of field in the given direction is defined as the difference of potential value wise upon separation, how much you walk.
Okay, sir.
And that's why this becomes minus dV by dr. So we call it a potential gradient. and the potential gradient is related to the component of electric field, which may be the net value as well.
Okay, sir.
So what we say that the field cannot be related to the potential directly, but we can always relate the component of a field with potential. Okay.
Yes.
So to make it more sophisticated, generalized, we'll try to create a general picture. So a relation between E net and V in Cartesian system. So
Sir,
what
all
we,
these,
yeah,
so
tell
the
me.
previous two were also proofs for the relation between E and
Yeah,
V.
all are relational only. So we'll just trying to make it a general value. So we were so far calculating only one component, right?
Yes, sir.
We are. So we are not aware of other component, right? At that point, if I walk in some other direction, I may get some other answer also.
Yes, sir.
So we got just one answer. Other answer I just ignored actually. So now I'm trying to make it general. So let's say this is the XYZ coordinate, and I choose a random point P where I again redraw the set of parallel axes, and I call it Y dash, X dash, and Z dash. Let's say the origin of this new coordinate system is itself is XYZ. So your point P is somewhere here. You're at some location having coordinate XYZ. So definitely this will have some potential which we can call V. Okay. Now we know that in three-dimensional world we just need three components to recreate the net vector. So if I know the X component and Y component and Z component, I can exactly know what is the E value. So I need three components, right?
Yes, sir.
So I can walk along the x-axis by a very small value dx. So let's say you walk x plus dx from the x coordinate, which is point P. Now I will expect the potential here to be different, and I'm calling this value as something interesting the way of writing. So let's say the potential is V, and now if the potential is changing at a rate of del y by del x, uh, if the rate of change of potential is del v by del x, which means if you walk along x, then it will change at certain value. So let's say this is your home. This road goes towards the town's best mall or the best location in terms of shopping. This road goes to the away from the city, maybe some rural background, maybe some villages, and this road goes to something towards the river, okay? Like where there is no person living, so it's like just jungle. So now, if you move towards this line, the cost of thing will change in a different way, right? So let's say if you want to buy something, or maybe some grocery or something, fruit or a vegetable, what do you expect? The price will grow very fast, isn't it?
Yes,
Because
sir.
you're moving towards the expensive area, like very downtown kind of thing. Okay. If you move towards the village area, the price will change not very rapidly, right?
Yes, sir.
So things which are easily available in the villages like fruits and vegetables, probably you will get at cheaper price. And if you go towards the jungle, you can get for free also, because you can get see the trees and everything, and you can just pick from there. So
Yes,
what
sir.
I'm trying to say that the potential will not vary in a similar fashion in all direction which we choose. So the partial derivative which we call del, so del v by del x is the variation of potential if you walk along x only. That's the meaning. So this is the rate at which things are changing. So you have a potential v, and if you have, this is the rate. So if you walk dx ahead, then what is the net change? Rate into dx. Is this clear?
Yes, sir.
And so we can add the component of field in this fraction, we can call it ex. So can we write ex as v minus v plus del v by del x upon dx?
Yes, sir.
So you have worked around by dx value. So what you can see here, so this turns out to be del v by del x only. So the partial derivative of the potential along the x direction gives the x component of electric field. And that's very simple, nice answer. So similarly, without even doing something like this, what we can talk about ey component. You have to work on y-axis. So the
Minus
answer
del
will
v
be
by
del
del
v by
y.
del y. And Ez will be,
Minus del v by del z.
so now because I have three components which are mutually perpendicular, and from the mathematics or the vector, we know if you have the three components in three-dimensional space, you can exactly recreate the original vector, which is E. So the net field at a point P, because I'm trying to find the net value, will be Ex I cap. This is the way of writing. So this turns out to be minus del V by del X minus del V by del Y. So EP vector equals to, so the way of writing this is also del by del X I cap, del by del Y J cap. And this term we have seen before in chapter of work energy power. This is called del operator.
Yes, sir.
So this del operator is minus, sorry, not minus, del by del X I cap. So we can write as the net value of electric field, we can write as minus the operator multiplied by potential. So this is the relationship between the electric field vector and the potential of a space in general. Okay. So when you walk along one particular direction, you get only one component. You will not get the net value. So net value may be different. Now, how you will come to know that this will have so many components, this will have less, this will have two, three, or just one? The answer is very simple. So if the potential depends on x, y, and z, all three coordinate, then you will have three component of electric field. If potential does not vary if you work along x-axis, if potential is not changing in the x direction, then we cannot have the field in the x direction, right?
Yes, sir.
So the only field will be along y and z. So we look
Yes, sir.
at the function, we look at the variable, and from there we deduce that which component might be absent. Okay. For
Okay,
example,
sir.
if I give you potential as x, just one dimension. If I give you only y, one dimension. If you give only z, even a very complex formula of x, y, z will. If I give you root x plus e power x plus ln x, so this is still one dimension, right? Why? Because the dependency is only on x variable, right?
Yes, sir.
So this we call one dimensional field. So what we can say that if v is a function of only x or only y or only z, it's a one dimension field. But if v is a function of either x, y or x, z or y, z, it's two dimension. And if v is a function of all three variable, it's a three dimensions. This is the 1D field, this is 2D field. It is clear?
Yes, sir.
Now, again, we have to think about the conservative. So a charge or any distribution of charge creates conservative field. That is, the field will be mostly radial or kind of diverging or converging, but it will not be circulating, which means it will not come back to the same point. So every field will have some starting point, some ending point, but the start and the end will not be same. Understood?
Yes, sir.
So now, how we prove a field is conservative? So we have done this before, so we can do it again. If I take the del cross E, the cross product of with the given vector, this is called curl of E. Curl means rotation.
Yes, sir.
So a field which is diverging, if you try to find the curl of diverging, it will give you zero answer. So it is same question as if a person is moving on a straight line and you're asking what is the omega, the answer will be zero. If the person is not seeing it, the point is moving. So if I am also on the same line as the particle is moving, I won't see any omega, right?
Yes, sir.
So for any conservative field, the rule is simple. For conservative field, the curl of the vector is always zero. You can prove it easily. So the proof is simple. You can take LHS del cross E, but E itself we can write as minus del V, which is same as del cross del.
Same direction.
So because the operator is same direction or same operator, so two operators or two vectors with the same value cross will be zero. So this is the famous law of electrostatics. The curl of a vector is zero, and it is always true for electrostatic field. the field which is developed by the charge particle or any distribution of charge. Okay.
Yes, sir.
So coming, okay, now let us go more further. So because we have derived the relation of E versus V, we can also relate the V in terms of, I mean, you can see the potential difference with electric field. So the next concept will be, we can remove this part, this is not a problem. So a relation between E and delta V, that is how the potential difference and electric field are related. So this is a very common question which you will come across again. So again, I will make a generalized derivation, which is easy for you. So if we have a random location, a random path in which you are moving, at the instant you may be here, at some later instant you may be here. So if I call this gap as a DL, because this is neither parallel to x-axis nor parallel to y-axis, I'm just naming it DL. Or you can also call it ds, but s generally refers to the areas or surface, so we want to avoid. So dl is a better way to represent. And let's say at this point the net field is pointed in this particular direction. So this is the net field in this direction. So if I draw a tangent, then the dl vector will be like this, and you can see the e vector. So let's call the angle between them as theta. Okay. So what we need to realize that E is the net field. Again, if I call the potential here as V, then potential we can call here as V plus dV. Okay. So the question is, what is the component of field in the given direction in which we are moving?
Sir, it closed. Yes,
So can we write E cos theta as V minus V plus dV upon dl?
yes, sir.
Remember, here we are only taking the direction of movement, and therefore we are taking the electric field in that direction.
Okay, sir.
So now we can clearly see the E cos theta turns out to be minus dV by dl. Okay. So the dV we can write as minus E cos theta dl. So if I integrate both sides, the difference is called potential difference, delta V. And on the right hand side, this is nothing but E dot dl. You can write like this. This is a very famous relation between the potential difference and electric field. And minus is representing obvious fact that as you walk along the field, the potential will decrease. So delta means change, which is final minus initial, so it will be negative answer. Understood?
Yes, sir.
So that's also logical. So now we have a certain formula that we have to, I mean, use right now to solve certain type of numerical. So let's do some practice. Okay. But before that, I have left one concept here in the equipotential. So I said that the electric field must be at the right angle to the equipotential surface. So let's try to prove it. Why? So why E should be why E should be perpendicular to the equipotential surface? The answer is pretty much simple. It is because if this is the equipotential surface, and if you say that no, the field is not perpendicular. So let's assume some angle. So by default, this is equipotential surface, EPS. So potential of this point should be how much? Same as this point, isn't it?
Yes, sir.
But by definition, E cos theta, we can write as V minus V
0.
by dx something, whatever you can name it, which is 0. So E cos theta is 0. We know that electric field is not 0. So what must be 0?
Component.
Cos theta,
Yes, sir.
which means theta must be 90 degrees. Understood?
Yes, sir.
The whole idea is if it is not perpendicular, then it will have a component, which means it can create potential difference across the surface, which is violation of the definition itself.
Yes, sir.
Understood?
Yes, sir.
So the electric field must be perpendicular to equipotential surface. Okay,
Okay, sir.
it is clear.
Yes, sir. Sir, the negative sign alone, can you just explain why it is?
Negative is like when we are deriving the answer, we know that along the field direction potential will decrease, right?
Yes, sir.
But E dot dl will give you positive answer, no?
Oh, yes, sir.
E is along the dl, so E dot dl will give you something positive if the angle is acute. Okay,
Okay, sir.
but we know the potential difference should be negative because along the field it should decrease.
Yes, sir.
So delta V always represents the decrease if you move along the electric field. If you move against, then E dot dl will be negative, so it will become positive automatically. So the minus sign will take care of both the direction, isn't it?
Yes, sir.
So I hope you understood why it is minus sign. Hmm?
Yes, sir.
So now we have to solve a large variety of numerical. So we'll start with simple problems. So example one. If I say that the potential at a point is given by minus 2x square plus 3, find electric field vector at 2 comma 3 comma like this. Can you tell me the answer? So it is which kind of field? The potential is changing only if you walk along x axis.
Axis. Sir?
Yeah. So potential is changing only if you walk along the x axis, right?
Yes, sir. So minus 8 I cap.
Yeah. So it will be plus 8, no?
Oh, right. Yes, sir. Minus dV by
Yeah.
dr.
So we know that the y and z component must be 0.
Yes, sir.
So we should only be worried about the x component, which is minus dv by dx, because it's one dimension. We can use the perfect or definite exact differentiation. So minus minus 4x, right?
Yes, sir.
And the x coordinate is 2, so the answer is 8. So the E vector coordinate is 8 I cap. Next problem. If I give V equals to x square y, plus y square. That's it. And I'm asking find the rectifield at -2 comma 3. Tell me the answer.
So
Yes.
12 I cap minus 10 J cap sum.
Okay. So first of all, we need to find the ex. And how much is ex? Minus 2xy.
Yes, sir.
And if I put -2, x is -2, y is 3. So it turns out to be 12, right?
Yes, sir.
And what is ey?
X square plus 2y.
X square plus 2y. With minus n, right?
Yes, sir.
4 plus 6. So the answer is correct. It is 12 I cap minus 10 j cap. Okay.
Okay, sir.
Now, if you want to find the net value, you can just take a modulus the way you know. The mod of E, if I want to know the value, it is under root of 12 square plus minus 10 whole square, which is 1 to 44 under. So whatever, I will not solve. So you can understand.
Okay, sir.
This is 2 root 61, right?
Yes, sir.
And the last question will be like when it is a function of everything. So if it is, um, okay. Find E at 1 comma minus 1 comma.
So,
Yeah.
sir, I'm getting minus 6 I cap minus 3 J cap minus 3 K cap sum.
So you're getting minus 6 I cap minus 6 j cap and plus
The
3.
minus, sir, minus 3 J cap minus 3 K cap sum.
All right. So So Ex you're getting as, let me just confirm, minus 2xy is 2xz square, right?
Yes, sir.
Yeah, so this must be correct. And the fourth question is, if I give you E vector as yi cap plus xj cap, if potential at 1 comma 1 is uh, 6 volt, find potential at x comma y.
Okay.
What happened to you?
Sir, just a second, sir. I just got the question.
It's the reverse question. The E is given, you're supposed to find the potential function, right?
Yes, sir.
Do it.
So,
Yes.
sir, I'm not getting like how to apply the limits when I am integrating some.
All right. So first of all, the formula that we need to apply is very simple. Delta V equals to.
Minus integral e dot. Yes, sir.
So now we can convert this into components because we have two variables. You can add a EX item and the DL we can also write as DX item like this.
Yes, sir.
Call from Mohit Singh Chauhan.
Just okay. So now this is the integration, right? Now the dv part is very interesting. So the way of writing this,
Sir, y dx plus x dy.
yeah,
For that integration, we did that already, sir.
yeah. So we have done this already. So this is like a you can add dv delta V has integration of dV, which is minus y dx plus x dy.
Yes.
And this is very famous, d of xy.
Yes, sir.
Now the limit is 1 comma 1. When the limit is 1 comma 1, this is 6. So when the x comma y, it is v.
So xy minus 1 is equal to v minus 6.
Minus xy minus 1, because this will have the equation, we know the answer. So
Yes.
1 is, and so v minus 6 is minus xy plus 1. So v equals to minus xy plus 7. Like this. Okay. So you will come across a variety of question like this, and now you're actually uh, able to now solve a lot question of, a lot more question of erodive. So from erodive, let me tell you what you can solve now, which I'll just mark it. So you can solve up to many questions. In fact. So if you look at the question 3 point, yeah, 3.48 onwards, all 3.48, 3.49. So your homework will be so these many questions you can solve. In fact, we have solved many in these questions also. Then you can solve. Sorry.
So we have completed the first part, sir.
No. We have to complete a lot more. Just a bit.
Sir,
3.3.
no, sir, that constant electric field and vacuum.
No, we haven't completed it. We have to complete a lot more things.
Okay, sir.
This is actually very vast chapter. I mean, there is no end to it. I'm trying to pull it as fast as possible. Let's see how much I can.
Yes,
So
sir.
this is the one part. So you just got the relations between everything. Now the next relation that you should be aware of. So the next question is called a relation between okay, change in potential and potential. I mean, this is like the topic is very difficult to quote, but what I'm trying to explain, you will understand easily. So let's say we have a system of charged particle, call it Q1, Q2, Q3. Imagine these three are the most dangerous, the wild dogs, the dogs, very dangerous.
Okay, sir.
So because these are three charges, so they will also have their own mutual potential energy.
Yes, sir.
But I'm not going to consider the same. Let's say there's a point P. The point P is at a distance R1, R2, R3 from these three charges. Okay. So definitely the three charges will contribute their own potential. So potential at point P will be equals to KQ1 by R1, KQ2 by R2, and KQ3 by. So this is called the net potential at point P. Okay.
Yes.
Now let's say a fourth charge or some next charge which is not part of system. This wants to be part of this system and wants to come at point P. Then how much work is required to bring this at point?
Sir,
So we know the
KQ1
answer.
by R1. Yes, sir.
Yeah. So we'll not do in that way, the way we have done. So what we know that the work done is basically the way we define is when you take the definition, the potential is defined as work done per unit charge.
Yes, sir.
So work done by external force is simply Q into the existing potential at point.
Yes, sir.
Call 91744350333.
Just one. So the work done by the external will be Q into Vp, and therefore you're not supposed to do anything. The definition itself will give you the answer because Vp is known to us. So this is QVp, and this is the work done, which is the additional work in adding the charge Q to the existing system. Okay. So can we say that this work will create or change the energy of the existing system by value QVp,
Yes, sir.
right? So when I say when we add some charge to an existing system, and if you know the location at which you want to like place, then the amount of work which you have to do additionally to place it is simply equals to Q into Vp, which is very simple way to remember. In most of the calculation, we simply write U equals to QV. Okay. But this U is the additional energy required to add charge Q to existing system. Okay,
Yes, sir.
understood. So the whole idea is now, I mean, the U of 1, 2, 3 plus U which you have added will be the, let's say the U mutual actually, this is U 1, 2, 3. So if I say the mutual potential energy of the three charges is this much, the work will actually give you the mutual potential energy of 1, 2, 3, and let's this is the fourth one. It is same thing. You have to understand what is happening here. We had this much energy, right?
Yes, sir.
This is the energy which you have to invest to bring the new charge into the system.
Yes, sir.
Okay. And if you take all four charges as one system, then their mutual will be actually sum of these two.
Okay, sir.
because now we have four charges, so four charges will have their own mutual energy, right?
Yes, sir.
So the difference we can always, so the Q into Vp actually gives the additional energy either given to the system or taken away from the system to add this extra charge to the system. Understood?
Yes, sir.
So now, if I create a hypothetical universe and I'm not showing you any charge, if I'm just telling you a fact that this is the point at which the potential is 10 volt, okay, and I want to bring a 2 coulomb charge from here to infinity to this point, then what is the volume required?
Sir, 20 joules.
That's a simple answer. Understood? So if you know the potential of a location is given to you, which is the net value, then any charge which you bring from the infinity will have this simple answer. So this is very crucial thing that we need to remember. So we write as the additional energy equals to charge into potential. So here the thing is the potential is defined for all other charge except this charge, right?
Yes, sir.
So now there is one more relation which we should be aware of. That's called the potential difference within electric and the work relation. There are so many relations. No? So the whole idea is if you have a charge, let's call Q, we know it will create potential everywhere, right?
Yes, sir.
So I choose two random point 1 and 2. And the potential at 1 will be equals to V1 and the potential at 2 will be equals to V2, which you can easily calculate for a given formula, but this is a general picture. If you take a charge particle from V1 to V2 through any random path, which it doesn't matter, then how much work is required?
V1 minus V2 into Q.
So generally we know the answer for the infinity, right?
Yes, sir.
So if I take a charge from here to here, the work we know is QV1.
Yes,
So
sir.
if I take a charge from here to here, the work we know is QV2. Okay. So what is the work, if you go from 1 to 2? So the work done must be
This
difference of
difference
difference of
between.
energy. So it's 2 minus 1, which is simply Q into V2 minus V1, which is final value. So when you move in the field itself, the relation is Q delta. So work done by the external force in taking a charge within the existing field is simply charge multiplied by difference of potential. So if you know the potential difference, you can easily get the work done. Understood?
Yes, sir.
All right. So this is the work done, and of course I have to put a star because we are moving it slowly. The other way of writing is work done by the system is minus Q delta. In case of system, it is negative sign, right?
Yes.
So now these are the various formula which you have to just manipulate and get the answer. You can always apply this one, which is very easy. Okay. The potential at infinity we take as 0, so you can always think potential as 0 and the point as v, the delta v becomes v itself. So when you move from infinity to a point, we call potential, but when you move from a point within the field to another point in the same field, then what we call is potential difference. So potential difference is for the movement within the field, and potential is always different from the movement from infinity to the point or vice versa. You can go reverse also. Okay.
Yes.
All right. So I think we're done with all formula. So what we can do next is so we have done the mutual potential. Imagine we have a simple question. So we have two charges which are fixed, but the third charge is not fixed. It is free to move. So if I release it, what will happen? See, once I release,
The repulsion, so it will move along the height direction.
yeah, along the resultant force direction, like this.
Yes, sir.
So once the free charge is released, it will start accelerating along the direction of net force. So as it will go away, the velocity of the free charge particle will increase.
Yes, sir.
Let's say m is the mass of the particle. So question is, what will be the net what will be the final kinetic energy of free particle? So think in the reverse process, you will get the right answer. So if let's say if the charge particle is at infinity, how much work you need to bring it here?
Sir, W into sir, the work will be Q into V, sir. The potential at that point.
Due to the two fixed charge, right?
Yes, sir.
So when the reverse phenomena will happen, then that energy will be given back to the same charge,
Yes, sir.
and that will eventually become the kinetic energy.
Okay, sir.
Understood?
Yes, sir.
So question like this we can solve just by the energy conservation. So what we can say that the energy possessed or the energy contribution of the bringing the third charge must be equals to less than, and this will eventually become the kinetic energy. In fact, you can also find the speed also at infinity.
Yes, sir.
So this is q into, and this will become kq by a 2 times is half mv square. So all right. So v square is 2 times 4 4 4 kq square by ma. So we can find v equals to. So a question like this can be asked with simple logic. So if you understand the definition, then only it is easy to solve. Else it is very complex. Like you won't get the idea what to do. So one must be able to see it. So when you bring the charge, if you have added the energy, so when it will go away, it will take away that energy which you have given. Okay.
Yes, sir.
The other way of thinking is that what is the initial mutual energy of the system? The answer is simple: 3 kq square by 8. But finally, because the third charge is not there, the mutual will be only between the first two. Okay.
Yes, sir.
So from conservation of mechanical energy, you can say U initial plus K initial of the system is U final plus K final, just by common sense, not applying by doing the basic calculation only. So U initially is 3 kq square by 8. There is no kinetic energy in the beginning. The final is this much, and in that the only particle moving is the third particle, so it will have the kinetic energy. So you can clearly see that it's the same answer, right?
Yes, sir.
So the choice is up to you. You can solve by both methods. So if you know what is happening, you can directly write. If you know, if you want to do it more, you can say detailed way, you can do it like this.
Okay.
So whatever you feel comfortable, okay, no need to worry.
Yes.
So imagine if I give you a situation like this. So we have a hexagon. Okay, so we have this charge. If I release the first charge, So you release the first charge, the first goes to infinity. You then release the second charge, which also goes to infinity. The question is, what will be the difference of kinetic energy of particle 1 and so just think about it, then you will get the answer. Always think in the reverse process. Let's say you bring the second, then first, or first, second, then what is happening? Like, what is the additional energy coming to the picture? So if you think in a reverse process, it's very easy.
So,
Yes,
sir, I'm getting the answer as KQ square by A.
that's the right answer. Excellent.
Yes, sir.
So
Sir,
it's
now
a
that
difference.
you
Yeah.
told, it just like,
Pardon?
sir, you kind of gave the clue, and then I just saw like
Ah.
for bringing the one charge and then bringing the other charge. There's just the other charge that's different.
Yeah. So the presence will, their own mutual is the difference.
Yes, sir.
Yeah. So the answer is also very simple, but it takes a lot of effort to think why it is happening. So These are some of the conceptual questions, and the rest will be very much straightforward. So you can start solving from resonance sheet, or even you can finish almost SC Verma completely, almost, except the dipole part. So
Yes.
in the next lecture, what I'm going to do is I'm going to take a lot variety of questions actually, and we have to also do the derivation of potential to continuous charge distribution. So the next target goal is in the next lecture will be, so first we'll do the calculation. So uh, calculation of potential due to continuous charge distribution. Okay,
Yes, sir.
this will be the heading. You can do the basic derivation on your own, but just in case if you want, you can wait for the next lecture. So we'll be finishing this. Hopefully now I think two more lectures we will be able to finish the not two, three lectures, maximum three, minimum two. We will be able to finish the electrostatics part one. Then we'll start the capacity.
Okay, sir.
Okay, so what about tomorrow?
Sir, yes, sir. So in the morning or the afternoon, sir?
Tomorrow I have so many lectures. I have morning lecture, then afternoon lecture, then also evening lecture. So it's very hectic tomorrow. Today is also hectic. Even right now I have one more lecture. So you can excuse for tomorrow. Then I can do it on Wednesday,
Okay, sir.
or maybe tomorrow. If I find some time in the afternoon, I'll let you know. Okay, so
Yes,
be
sir.
ready. Be ready in the afternoon part, like maybe from 2 to 5 part, or maybe 2 to 6.
Okay, sir.
Okay, so I'll let you know. I'll let you know.
Yes, sir.
Good night. Take care.
Good night, sir. Thank you, sir. Bye, sir.